in your course and in NIT as well. And I will teach you the fourth unit, advanced material actually. Okay? Hello?
Yes, sir.
Yes, sir.
Okay.
Yes,
So
yes,
I
sir.
will
Yes,
teach
sir.
you the unit 4, advanced material, especially dielectric material. Okay? So let me share the screen. Okay. Are you getting the shared screen?
Yes, sir.
Yes,
Yes,
sir.
sir.
Yes, sir. Yes, sir.
Yes, sir.
So as I told you all, I will teach you the dielectric materials. Okay, lecture first and the unit 4. Okay, so before starting the dielectric material, we should know what are the conductors actually. What are the difference between conductor and the insulator? At the material classified in two ways basically, conductor or metals and the insulator. So what are the conductors? Conductor that can conduct electricity without any resistance. Okay? Without any opposition. Okay?
Yes,
Clear?
sir.
So that's why we
Yes,
can
sir.
say that conductors or metals have the free electrons. Okay? In the conductors, the electrons are totally free. Okay? No electron is bound with the other interactions. Okay? So that's why we can say that the conductors have the free electrons. Okay, this is the main reason behind the conductivity of the conductor. Okay, that we never get from the insulator because in the insulator the charges are not free. Okay, clear?
Yes, sir.
Yes, sir.
Okay. So everything should be clear, especially in the physics. Okay, every concept should be clear. Okay. So then what are the dielectrics? The one question arises in our mind, what are the dielectrics basically? Some people says that the dielectrics are the insulator. This is good. Dielectrics are the insulator, but all the insulator can never be dielectric. Okay? It will be discussed later, but in the starting, the dielectric are just the insulator or non-conducting material. Okay? As the dielectric can store the electrical energy, we use the dielectrics in capacitor, memories, and the sensors, etc. Okay? So my question is that what is the actual meaning of the dielectric? The dielectric are the insulator which hold the bound electrons, not the free electrons. Okay, as we seen in the conductor generally has the free electrons, but dielectrics are the substance which do not contain free electrons, or the number of free electron is too low to constitute the electric current. Okay, is it clear?
Yes,
Yes,
sir.
sir.
Yes, sir.
Okay.
Yes, sir.
So
Yes,
that's
sir.
why finally we can say in the dielectric, the electron are totally bound to the nucleus of the atom. But another question is arises in our mind, what is the bounding? What is the bounding? How the electrons are bound with the nucleus? As we know, the nucleus has the positive charge and the electron has the negative charge. There must be a coulombic action. There must be a interaction in between the electron and the nucleus. Okay? Were the best examples of the dielectric mica, glass, plastic, water. Water is the best example of the dielectric, and we will be discussed later in the next slide. Okay, etc. Okay, so everyone can get shock, electric shock in the water but the water is insulator. Okay, so how we can get the electric shock? Because water has the dielectric property. Okay, it can conduct electricity via the bound electron system. Okay, so what is the difference between dielectric and insulator? Dielectric materials able to store electrical energy. Insulator, what are the insulator? Insulator suppose the electric current. Okay, we can never say all the insulator are dielectric, but all the dielectrics are insulator. Okay, So keep in your mind, all the dielectrics are insulator, but all in the insulators need not to be dielectric. Okay? So, okay? Now, what is the application? What is the scientific application of the dielectric? The electric material is capable of storing the electrical energy due to polarization. Okay? Don't be confused with the polarization. Okay? Okay?
Yes,
I
sir.
will teach. I will tell you more about the polarization in the next slide. But here
Pardon
you
me,
should,
sir.
you should know at least the dielectric material is capable of storing the electric energy. Okay?
Pardon me, sir.
Okay.
Hello.
Ji, hello.
Sir, most of the students I want to still join the class. Let them in.
Okay, no problem. Okay.
Let them in, sir.
Okay. Okay. I think they are joined now. Okay.
Okay.
Okay. So in my class, okay, keep in your mind you have to come on time. Okay, 10:30. Okay,
Yes, sir.
Yes,
okay, you
sir.
have to
Yes, sir.
come on time.
Okay, sir.
10:30 a.m. Okay,
Okay, sir.
Okay, sir.
okay, because it may create some disturbance for the others. Okay, yeah, okay. So how we can store the electrical energy? As we know, as you studied earlier, is the capacitance. So what is the capacitance? As you studied in the 12th, the capacitance in the parallel plate capacitor. So C is equal to F sin A upon D. The capacitance is decreases as we decrease the separation in between the plates. Okay, so this is one thing. And the other thing, how we can increase the capacitance? We can increase the capacitance by increasing the dielectric constant. Okay, each dielectric material has the dielectric constant. If we increase the dielectric constant, then we can increase the capacitance and we can store the more electrical energy in our system. Okay, is it clear? So you can see here in this picture how we can increase the dielectric constant. Okay. Then in the next slide, these are the basic terminology of the dielectric material. What are the main factors that are responsible for the dielectric material? Okay. What is the dipole? Other is the dipole moment, and then the dielectric constant. Okay. And hope you are well aware about the dipole. Okay. What is the dipole? A dipole is a system of two equal and opposite charges separated by a small distance. Okay. Why we call the small distance? What is the meaning of the small distance? There must be an Coulombic interaction between the opposite charges. Okay, as you can see here, Q and Q minus Q is separated by a small distance. Okay, there must be a Coulombic.
Pardon me, sir.
Okay, hello.
Still one, two students haven't joined the
Okay, okay,
class due
okay,
to network issue. So please last
okay,
time
okay,
admit them.
okay. I think joined. Anyone else? Hello? Hello?
Yes, no,
Anyone?
sir, I don't think so.
Okay. 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 And other is the dipole moment. What is the dipole moment? The product of that one of the charges into the separation between them. And what is the unit of the electric dipole moment? To Coulomb into meter. Okay, and come on the dielectric constant. So what is the dielectric constant? Dielectric constant is nothing. The dielectric constant is just the ratio of the electric permittivity in the medium to the electric permittivity in the free space. Okay, it is just the otherwise we can also determine the dielectric constant in terms of the capacitance, because the capacitance is directly proportional to the K. Okay, so that's why we can determine the ratio of the capacitance in the medium to the capacitance in the free space. Okay, so hence the dielectric constant is the ratio between the permittivity of the medium to the permittivity of the free space. Okay, so what is the electrical permittivity of the free space? In the free space, what is the value? 8.85 into 10 to the power minus 12 farad per meter. Okay. Now, to discuss the dielectric material, you should know more about the three main parameters. Three main parameters are, we can say, the vectors E, D, and P. Okay. You studied earlier E, and what is the D? Okay. E is the electric field intensity, and D is the electric displacement vector, and P is the polarization, and that to be discussed in the next slide. Okay. The electric field intensity. Okay. Everything you are well aware about the electric field intensity. Electric field intensity you can determine using the Gauss law. Okay, it is nothing. The force experienced by unit trace charge is known as the electric field strength. Okay, everything is well known. Okay, this is not a big thing. Okay, so now this is the equation first. And what is the electric displacement vector? Okay, actually you can use the terms E for all kind of charges. All kind of charges you can use the word E. But what is the electric displacement vector? The electric displacement vectors are only for the free charges. Okay, free electrons. Okay, so that's why we can define the electric flux density or electric displacement vector is the number of flux line crossing normal to a unit surface area. Okay, number of flux line crossing normal to a unit surface area. So that's why the electric flux density at a distance from the point charge you can determine D is equal to Q upon 4 pi r square. 4 pi r square is the area, surface area, and Q is the charge. Okay, and in the equation first you can see that in one more parameter, epsilon naught. Epsilon naught is the electric permittivity in the free space. So after combining the equation first and two, we can get the equation D is equal to epsilon E. This is the main equation, and keep in always mind what is the D. The D is equal to epsilon naught E, and directly proportional to the capital E. As well as we increase the value of the E, the T also increases. Okay. What is the electric polarization? This is main thing responsible for the dielectric constant and the dielectric material. The phenomenon of producing electric dipole by an electric field is called polarization. So electric polarization is nothing. It is just producing the electric dipole by an electric field. It's called the polarization in dielectrics. As you can see in this picture, in two plates of opposite charge plates, plus and minus one, and we kept an dielectric atom. As you can see, the direction of the electric field from the positive to negative. That hence the positive charge will move along the direction of the field, and the negative charge, as you can see by the dot, okay, moves opposite to the electric field, hence creating the electric dipole. Okay, thus the phenomena of producing dipole by an electric field is called polarization in dielectrics. Okay.
So can you add some more students? They are waiting.
Hello.
So can you admit some more students?
Okay. 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 So these are the main parameters E, D, and P vectors. Okay. Any doubt? Anyone has any doubt? Okay. Now come to the polarizability. Okay. The polarizability actually is the characteristic of the material. So what kind of material we are using for the dielectric? Okay. The polarizability is the material property. Okay. Okay. The induced dipole moment per unit electric field is called the polarizability. Okay, the induced dipole moment per unit electric field is called the polarizability. As we increases the value of the electric field, thus induced dipole moment will increases. Hence, we can say mu is directly proportional to the A. Mu is equal to alpha A. Alpha is the proportionality constant and basically known as the polarizability constant. Okay, if it is the equation for the one atom, but if the material contain n number of dipole per unit volume, then mu is equal to n alpha I. Okay, if you want to determine the polarizability in case of the n numbers of dipoles, okay, so just we can multiply by the n. Now, the polarization vector, the completely how we can write the polarization vector, the dipole moment per unit volume of the dielectric material is called polarization vector. Okay, it is just the dipole moment per unit volume is known as the polarization vector. Okay, now we have to write the displacement vector equation in free space other than the medium. Okay. So electric field density, it is equation number first, as I told you in the previous slide. Okay, D is directly proportional to the E. This is the equation for the free space. And at the same point in a medium, if we are talking about the medium, then we can write the D is equal to epsilon E. What is the difference in between? Here we have taken the epsilon naught. Okay, in here we have to take the epsilon. Epsilon is the electric permittivity in a medium, and epsilon naught is the electric permittivity in free space. Okay, as the polarization measures the additional flux density arising from the presence of material as compared to the free space, then we can finally write the we can finally the relation third using the relation 1 and 2. D is equal to epsilon E plus P. This is the main equation responsible for the polarization. Okay, as well as the dielectric constant. Okay, so D is equal to epsilon E plus P. Okay, is it clear? This is the main equation. Keep in always your mind. D is equal to epsilon E plus P. D is the displacement vector, E is the electric field, and P is the polarization vector. On the basis of this equation, we can analyze all kind of dielectric material. Okay, we should know at least the equation number third. D is equal to epsilon E plus P. Okay, is it clear?
Yes, sir.
Yes, sir.
Okay. Now we have to do some mathematics to derive some relations. Okay. So it is nothing. Okay, no problem. So D is equal to epsilon I plus P using equation 2 and 3. So D is equal to epsilon. Actually, we put the D value of the D. D is equal to epsilon E. As you can see, D is equal to epsilon E. D is equal to epsilon E by substituting. So by substituting the value of the D, okay. So here, after solving the equation, you can get the relation. Relative permittivity. Relative permittivity is nothing. It is the dielectric constant. Okay, dielectric constant. Epsilon R, epsilon naught minus E. After simplifying, okay, you have to simplify this equation. Okay, you all. Okay. Epsilon R, epsilon naught minus epsilon E, epsilon naught E is equal to P. Hence, we get the relation P is equal to epsilon R minus 1, epsilon naught E. Okay, where we put the epsilon is equal to epsilon R relative permittivity epsilon naught. Okay, now it is just the mathematics. Okay, now dielectric susceptibility, other main components of the dielectric material parameter. So what is dielectric susceptibility? Actually, the quality of the dielectric material that is to be polarized. Okay, how we can know the quality of the dielectric material? Okay, what is the quality of the dielectric material that we have used? Okay, then the electric susceptibility chi are responsible for the quality of the dielectric material. Okay, and as we can see, the polarization is directly proportional to the electric field intensity E. Okay, hence the proportion, there will be some proportionality constant, and the proportionality constant is the electric susceptibility. Okay, the chi is equal to P upon epsilon naught. Okay, now if we are simplifying this equation, P is equal to P upon epsilon RT, then we can write the chi is equal to epsilon R minus 1. This is the other main equation. Chi is equal to epsilon R minus 1. Okay? Is it clear? So chi may be positive or negative. Okay? Depending on the nature of the dielectric material. Okay? It may be paraelectric or ferroelectric, and that has to be discussed later. Okay, but here the chi may be positive or negative depending on the value of the dielectric constant. Okay, if the value of the dielectric constant is less than the 1, then you can get the value of the negative value of the dielectric susceptibility. Okay, otherwise if we take the value of the dielectric constant more than 1, then we can get the positive value of the electric susceptibility. Okay, so what type of the polarization? Okay, there are 4 main types of polarization, or the polarization phenomena: electronic polarization, ionic polarization, orientational polarization, space charge polarization. Okay, as you can see one by one, the electronic, atomic, orientational, interfacial. Actually, you can see the electronic polarization in atoms. Okay, especially the inert atom, monatomic gases, inert gases. Okay, and the ionic polarizations you can see in the molecule, where there must be an interaction between the atoms. Okay, the molecule. What is the molecule? The molecule is just the group of the atoms. Okay, and then orientational that has to be discussed in the next slide. Okay. And the next, the interfacial polarization. Now we start from the electronic polarization. Okay, so what is the electronic polarization? Okay, actually electronic polarization, we can see the electronic polarization basically in monoatomic gases, more especially the inert gas atom like helium, neon, krypton. Okay, so what is the electronic polarization? When an electric field is applied to an atom, positive charge nucleus displaced in the direction of the field, and the electronic cloud in the opposite direction. Okay, before applying the electric field, the center of the positive and the negative are coincident. Okay, but after applying the electric field, the positive charge will move in the direction of the field, and the negative charge will move in the opposite direction of the electric field, hence creating the electric dipole, always the dipole moment. Okay, so this is the polarization actually. Okay, hence what is the polarization? Polarization creating the electric dipole moment per unit volume. Okay, okay, when we are talking about the volume, then there must be a polarization. The dipole moment is proportional to the magnitude of field strength and is given by the dipole moment is directly proportional to the E, as I told you in previous slides. So mu is equal to alpha E. What is the alpha E? Alpha E is the electronic polarizability constant. Is it clear? Now, it increases with increases the volume of the atom. Okay? Okay? Yeah, I will discuss why the increase the electronic polarizability with increasing the volume in the next slide. Okay, so this kind of polarization mostly exhibited in the monoatomic gases. Monoatomic gases, like especially in
Excuse me, sir.
inert gas atom. Okay.
Hello.
Hello.
So polarizability is inversely proportional to volume, right? So
Yeah.
how it is going to increase with increase in
Polarizability.
volume?
Please repeat.
So polarizability is a total
What is your
dipole
name?
moment
What
per
is your
unit
name?
volume, right? So
What is your name? Sujal. Please repeat.
So polarizability is total dipole moment per unit volume, right?
Polarizability. No. Polarization. Polarization vector actually. Dipole moment per unit volume, not polarizability actually. Okay. देखिए polarization is a general word. Polarization can occur in all kind of materials, but polarizability depend on the nature of the material. Okay, clear?
Yes, sir.
Okay. So, okay, so this kind of polarization would be between monatomic gases. Okay, hence we replacing the polarized value of the polarizability for that kind of material. As I told you, Sujal, polarizability is the characteristic of the materials. The helium, neon, argon, krypton, depending on the size of the atom. As we increasing, as you can say here, the helium, neon, krypton, neon has the largest size as compared to the helium, and the krypton as compared to the neon, and krypton as compared to the argon. So hence, as we increase the radius of the atom, thus we increasing the in electronic polarizability 0.18, 0.35, as you can see here, there is an increasing manner of the polarizability. Okay, but there is some limitation for the polarizability of all kind of polarizability. Electronic polarizability occurs only at optical frequency. We can get the electronic at the high frequency or the optical frequency 10 to the power 15 hertz. Okay, it is independent of the temperature. Okay, it never depends on the temperature. Okay, so this is the expression. This is some mathematics. How we can determine the expression for the electronic polarization. As you can see here, before applying the electric field, the center of the positive and negative charge coincide. But when we are applying the external electric field, okay, there must be some where the positive nucleus will move in the direction of the electric field. Okay, so hence separating by a small distance and creating that electric dipole. Okay, when you are applying the electric field, so what kind of the force will act? Lorentz force. F is equal to QE. Okay, I will tell you in the next slide. Okay, will balance the Coulomb force. Okay, what is the reason of the Coulomb force? The Coulomb attraction force due to the opposite charges of these particles. Okay, the electron has a negative charge and the nucleus has the positive charge. Okay, there should be balance the Lorentz force. Okay, how we can derive the relation? It's very simple. Okay, this is the atom before applying the electric field. Okay, we can determine the surface charge density. To ZE, we have to determine negative charge for the electron charge density ZE upon 4 pi r cube. Okay, but we have to determine the charges on the small sphere inside this big sphere with the radius x. So how we can determine that? If you know the charge density, you can determine very simply. So thus the negative charge in the sphere of the radius x is q is equal to charge density into 4 upon 3 pi x cube. Okay, is it clear? Is it clear for everyone? Okay, actually we are just determining the value of the charge in the small sphere, as you can see here in this picture. Well, okay, so this is a big sphere, as you can see in the red portion. Okay, we have determining the small sphere of radius x. Okay, so q is equal to, after simplifying the equation, we can get the relation minus ZE upon RQ upon x cube. Okay, now I told you, okay, there must be a compensation in between the Coulomb force and the Lorentz force. What is the Coulomb force in between the positive negative charges? There must be a Coulomb force. Fc is equal to 1 upon 4 pi epsilon naught QE and QP. QP is the charge of the nucleus, QE is the charge of the electron, separated by a small distance x square. Okay. Okay, but and substituting the value of QE from the equation first in the equation 2. Okay, then we finally get the relation minus z square e square x upon 4 pi epsilon naught upon RQ. Okay, in the next slide, as I told you, the Coulomb attractive force will balance the Lorentz force at equilibrium. So thus we can find out the relation alpha naught electron polarizability is equal to 4 pi epsilon naught r cube. Okay, this is the final relation of the electronic polarizability. And I told you in the previous slide, the electronic polarizability increases by the size of the atom, as you can see in the last slide, previous slides. Okay, as we increasing the size of the atom, then the electronic polarizability increasing as well. Okay, hence the electronic polarizability is directly proportional to the cube of the radius of the atom. Okay, okay. So you have to keep some relation in your mind, the main equation. So this is the main equation. What is the equation of the electronic polarizability, the electronic polarizability 4 pi epsilon naught upon r cube. Okay, if someone if someone gave you a value of the size of the atom, then you can easily determine the value of the electronic polarizability. Okay, and next come to the ionic polarization. Okay, electronic polarizations occur in the monoatomic gases. Okay, for the atom, but the ionic polarization occur in the group of the atom. What is the meaning of group of the atom? Molecules. There must be some interaction in between the atoms. Okay, okay, but in the electronic polarization, not any kind of interaction between the atom. Okay, we especially talk about the free atom, but in ionic polarization, we talk about the molecules. Okay, so how we can get the polarization in the molecules? Then we have to use the word ionic polarization. Okay, the ionic polarization mainly due to a relative displacement of the atomic component of the molecule in the presence of the electric field. Okay, so when a electric field is applied to a molecule, the positive ion displaced by x1, as you can see in the picture. This is the case. This is the special case. I have taken the special case of the sodium chloride. Sodium Na positive is a cation and Cl negative is the anion. Okay, this is the best example to understand the ionic polarization. After applying the electric field, okay, after applying the electric field, the sodium cation will move in the direction of the electric field, and the chlorine negative ion is opposite direction to the field. Okay, so there must be a two displacement x1 and x2. Hence, the resultant dipole moment may be is equal to q x1 plus x2. This is the expression of the electric dipole expression for the ionic polarization. Okay, so restoring force. If we are applying the electric field on NaCl, okay, there must be a restoring forces in terms of the F is equal to Kx. Okay, as you studied in the elastic property of the material, the restoring force constant depend upon the mass of the ion and natural frequency, as you can see in this picture, and balance the Lorentz force. Okay, hence we can determine X is equal to E m omega square. Here there are two. Here they are cations and anions and different masses. Then we can find out the m is equal to 1 upon m1 plus 1 upon m. Okay, 1 upon small m is the mass of the. Actually, we cannot say exactly here. I am not specifying the masses of the sodium chlorine. I have just taken the small m and the capital M. Okay, so no problem. So X is equal to E upon M, E Lorentz force upon M omega naught is the natural frequency. Hence, we can derive the relation in terms of two masses x1 plus x2. So E upon omega naught square 1 upon M plus 1 upon M. Then finally, the induced dipole moment V on it E is equal to x1 plus x2 charge into separation. Okay, hence V is equal to ionic, and then finally we can get the ionic polarizability V ionic upon E. This is the ionic polarizability. Okay, this polarization occurs at a frequency 10 to the power 13 Hertz infrared region. Okay, as I told you in the previous slide, there will be some limitation of the frequency. Okay, this polarization occurs at the frequency 10 to the power 13 Hertz. So keep in your mind. If someone asks about what is the frequency range for the case of the ionic polarization, okay, then this polarization occurs at a frequency 10 to the power 13 Hertz. So, okay, it is slower process compared to the electronic polarization, and like the electronic polarization, it is also independent of the temperature. Okay, before going the next orientational polarization, we should know about the what are the non-polar and the polar dielectric molecule. Okay, so what are the non-polar dielectric molecule? Where the center of the positive and negative charges are coincide, known as the non-polar. Okay, such kind of dielectric materials never show any kind of dipole moment because the center of the positive and negative charge are coincide. But what is the polar? In polar, there must be some separation in between the positive and the negative. Okay, hence creating the dipole, and has the permanent dipole moment. Okay, so non-polar dielectric material has no permanent dipole moment, but polar dielectric materials has permanent dipole moment. Okay, as I told you in starting my lecture, water is the best example of the polar dielectric material. As you can see in the picture, H hydrogen is the plus and the oxygen has the negative charges, hence creating the some small distance. Okay, and therefore producing the dipole moment. Okay, okay. Then what is the effect of the electric field on the such non-polar or the polar dielectric? If you are applying if you are applying the electric field on the non-polar dielectric material, then such kind of material show the induced dipole moment. Hence, we consider the polarization electric dipole moment per unit volume. Okay. Now comes to the polar dielectric material. What kind of polar dielectric material? Polar dielectric, in the absence of polar dielectric material, shows the permanent dipole moment even in the absence of the electric field. Okay, but we always get the minimum dipole moment. Hence, we can ignore the induced dipole moment provided by the such polar dielectric materials. But after applying the electric field, okay, after like the all the dielectrics are oriented in the direction of the fields. Hence, producing the total dielectric. Hence, producing the total dipole moment. Is it clear? Okay, what are the non-polar and the polar dielectric materials? Non-polar dielectric material has no permanent dipole moment, but polar dielectric material has some permanent dipole moment. But we never get the dipole moment because it has a very small value. We can ignore the such value. But after applying the field, all the dipole oriented in the same direction, and we can produce the total dipole moment. Now come to the orientational polarization. Okay, as we can see through the name of the orientational, that we can understand easily. Orientational is orientational. Okay, the electric field can orientate the dipole. Okay, so it is also called the dipolar molecular polarization occur in the molecules such as H2O, N2, oxygen, Cl2S, like this. Okay, okay. Okay, is it clear? So you can see in this picture, however, the net dipole moment is negligibly small since all the molecular dipole are oriented randomly where there is no electric field. In the presence of the electric field, these all dipole orient themselves in the direction of the field. As a result, the net dipole moment becomes enormous. Okay, it occurs at a frequency 10 to the power 6 hertz to 10 to the power 10 hertz. It's slow process compared to any process. It is slow. Okay, so it's greatly depend on the temperature. Okay, among the different kind of polarization, the orientational polarization depends on the temperature. Okay, how the orientational polarization depend on the temperature? We can see the equation. Okay, no need to go more about the mathematical expression. You have to keep in your mind. This is the final relation. Okay, what is the polarizability, orientational polarizability? Mu orientational pan KT. Okay, as you can see in this equation, the orientational polarizability is inversely proportional to the T. Okay, so what is the reason? What is the reason? Why is the rotational polarizability decreases with decreasing the temperature? Actually, after applying the some temperature in the system, okay, we can get the some extra energy. Okay, okay, we can get the some extra energy using the relation, using the thermal equation E is equal to KT. Okay, that get randomly oriented the dipole moment, hence decreases the value of the orientational polarizability. Okay, now the total polarizability in the dielectric material, it is just the sum of the electronic polarizability plus ionic polarizability plus orientational polarizability. At low frequency, we always get all kind of electronic polarizability. Okay, in terms of electronic polarizability, the ionic polarizability is the orientational polarizability. So hence, this is the final expression. Keep in your mind Okay, always keep in your mind for the future when someone is asking about the total polarizability of the dielectric material. कि 4 pi epsilon naught upon r q is square upon omega naught q square 1 upon m plus 1 upon m and plus the orientational polarizability. Okay, and one more thing. What is the temperature dependency? The electronic and ionic polarization never depend on the temperature, but rotational polarizability always depend on the temperature. Okay, so this is called the Langevin-Debye equation for total polarizability in dielectrics. Okay. Okay, as I told you, this is the frequency dependent of several contribution to the polarizability. Okay, and this is very important. Frequency dependence of several contribution to the polarizability. Okay, as you can see one by one, at low frequency, I can say below the microwave frequency, we get the all kind of polarizability. But as we increases the frequency towards the microwave, then dipolar orientational polarizability ceases fast, and we get remain the ionic and electronic polarization in between the microwave and the infrared.
Sir,
Okay.
sir, I have a question. Sir, I have a
Yeah,
question.
yeah.
How can you generate this type of wave? This is a certain mathematical equation or not?
No, actually this is experimental graph actually. Okay. Actually at your level, you can understand this graph actually, but in the next higher class, you can understand better how we can draw this graph actually. Okay. This is an experimental assumption.
So this is experimental.
Yeah, experimental. In general, actually the dielectric constant always decreases the frequency. Okay. Okay, but like this study you will learn in the next higher class. Okay. Okay. But here
Okay.
you can understand what are the frequency dependence of the several contribution to the polarizability. Actually मैंने आपको समझाने के लिए इसमें लगाया है. ठीक है? The how the frequency dependence of the several contribution to the polarizability. Okay, at the infrared we get the two kind of polarizability, ionic plus electronic, and then the case is again the ionic polarization will increase the frequency toward the ultraviolet or the optical region, and then finally in the optical region we can get only the electronic polarization. I use this graph only to understand, okay, clearly what is the frequency dependence of the cell contribution to the polarizability. Okay, okay. Actually, graphical method is better than the mathematical expression. Okay, I hope you all are well understood about the frequency dependence of the cell contribution to the polarizability. Okay. Okay. I hope. Okay.
Yes,
I
sir.
think I should stop here. It is 2 and a half. Okay. So
Yes, sir.
Thank you, sir.
Okay, sir.
Thank you, sir.
you can take help from the group.
Upload the PDF of the notes, sir. Google Class.
Yeah. I will provide. Okay. I will upload.
Sir, attendance. Okay, sir.
Okay, attendance. And who are the CRs of this class? Who are
Sir,
the
it's
Yes,
me,
sir.
Shivam and
Attendance.
Shivam and Samriddhi.
actually? Please send the names of there on my WhatsApp number directly. You can send. Okay.
Okay, sir.
Okay, and send me the attendance. Okay.
Okay, sir.
Okay.
Okay, sir. Okay.
Is there any doubt?
Sir, can you send a PDF of any one
Yeah,
of
of
the
course. Yeah.
of the physics
I will upload.
textbooks?
Okay. Yeah. Of course. I will send. Okay.
Okay, sir.
I will send along with these notes. Okay.
Okay, sir.
Okay. Thank you. Bye.
Okay, sir.
Thank you, sir. Bye, sir.
Thank you, sir. Bye, sir.
Okay, sir.
Thank you, sir.
Sir.